Our third speaker is David Martinez. I'm very happy to introduce David as a co-author, and he's one of several graduate students who will be speaking at this conference, and he's going to talk about metric dimensions and minors.
Hi, my talk's on the metric dimension and minors of a graph. All our graphs here are simple, connected, and undirected. So first I'm going to start with talking about, sorry. First I'm going to start by talking about the metric dimension, which I don't think I have to that much. And then the excluded minor class, and then operations relevant to the excluded minor class, and then results that we were able to get based on the operations. So the metric dimension was introduced by Slater and Harry Metler independently. They both had different reasons why they wanted to do it. I can't remember quite exactly why now. But the metric dimension seeks to answer how many vertices are needed to uniquely determine all the others by distance. So I'm going to give the intuitive definition. Take a graph with some vertices. We're going to choose a subset of them. We're going to label them. And then for any other vertex, we're just going to take the distance. Okay, and this is going to give us a distance vector. And we're going to do this for all the other vertices as well. And we say that W is a resolving set if all the distance vectors are unique. Okay, and then the metric dimension is just the minimum W that we can find that resolves the whole graph. Okay. So here's a more formal definition. We say W resolves U and V if the distance from U is different from the distance to V. Okay. So here's an example. We have this labeling. Then W does not resolve U and V because the distance is the same for both. If we have this labeling instead, then W does resolve U and V as their distance vectors are different. Okay. So for example, A star, we can see that it gets harder and harder. For example, if we choose the middle vertex instead of this one, we chose the middle one, then everything else is just one. Mostly when you choose a resolving vertex, you kind of want it to distinguish itself. It's always going to distinguish itself. So you want it to at least distinguish another vertex. Okay, if we chose the middle one, it will only distinguish itself. Okay. So if we choose another vertex, we can see that we get this kind of pattern. And eventually we can see this has metric dimension 4. Okay. So what makes the metric dimension hard to compute? Well, it's a NP complete problem, but also it just requires checking way too many subsets. And it's very unreliable. For example, we have this graph, which is K24, just two independent sets here, two vertices in an independent set and 4 vertices in an independent set on the other side, and just attach them each. Then this has metric dimension 3. But if we were to add this edge instead, it can go down to 2. But if we add this one instead, it can go up to 4. And if we added this one, it can stay at 3. There's many results for many families of graphs. For example, the path, the star, complete, and so on. Okay. Is there any questions? Yes.
So I just want to get a feel for like why this is called dimension. Is the idea that I'm just thinking like the metric dimension is 5 or something, then you could put each distinguishing vertex like could be an axis, and then every
like a lattice. I think when we try to compute something else called the Dressel dimension, we kind of want to put it like in the lattice plane, I suppose. And I'm assuming that's why it's called the dimension. So yeah. Oh, sorry. Was there any other questions? Okay. So here are definitions. For example, planar and outer planar graphs. A graph is just called planar if it can be drawn without any edges intersecting. Okay, and outer planar just means that all the vertices lie on the outer face. I'll give an example. And then we say it's maximal if no additional edges can be added without losing its planarity. For example, this graph is planar, but it's not outer planar. If we try to move the middle one somewhere else, then we always get, then we can never draw it in a way where all of them are touching the outer face, which is the blue. But here, this is outer planar and it's also planar. Okay. And every outer planar graph is, of course, planar. So what is a series parallel network? It's just a graph that can be made from a vertex with a loop. And we just do two operations, which is either adding an edge. Here we can also add a self-edge, or adding vertices on an edge, as many as we want. Okay, so for example, here we add this edge, and we just add these vertices, and we can continue doing these two operations over and over again. So any graph that can be made from this is called a series parallel network. Okay, and these are two more operations. One is really easy, it's just the edge deletion. And the other one is just the edge contraction, where we pick two vertices, and the edge between them, we kind of clamp them together. And so we get something like this. Okay, any questions? Okay, so what is a minor of a graph? A minor of a graph is just any graph that can be made from a graph G by deleting or contracting edges. And we denote EX to just be the excluded minor class. And when we have the graphs inside, we just say that this is any class of graphs that do not contain the GIs as a minor. Okay. And they categorize what is exactly inside some of these minor classes, excluded minor classes. For example, a forest is just a trees connected together. Well, not connected, but side by side, I guess. And a tree doesn't have a cycle, so it clearly cannot have K3 as a minor. Okay, and then there's other families as well. So here are some known results. Diaz and friends in 2017, they kind of showed that the metric dimension can be solved in polynomial time for outer planar graphs. Okay, and then Queens and Sun in 2017 also proved that the graphs are bounded above. They also showed that for maximal outer planar graphs as well. Okay, any questions? So what's our main goal? Our main goal is to determine what exactly is in the excluded minor class of series parallel networks. But this seems a little bit hard to actually find. So we want to get some general bounds for any minor class for now. But what exactly lies in here? Well, as we said, it's anything with edge deletion and edge addition. And we know that they're inverse operations of each other. We also want edge contraction, but what's the inverse operation of the edge contraction? Well, this is where we come with a vertex split. Suppose you have this piece of a graph. If we want to split V, we just create another vertex, attach it, and then just partition the neighbors of V. So we can get many types of vertex split. Okay, and we denote with this operation. So here are several examples we can get. We can partition them as we want. It can also be empty and so forth. So now we know that we have the edge deletion, edge addition, edge contraction, and vertex split. But there's more that we can find. For example, if we take two graphs inside our excluded minor, then we can also kind of connect them or amalgamate them. And this is called the vertex amalgamation. Okay, so we also need to figure out this operation. Okay, so we have these 5 operations that we kind of have to know how to deal with in terms of the metric dimension. Okay, so these are our results. So for the vertex amalgamation, we were able to bound it above and below. I'm going to give a sketch proof of this. So suppose this side has P resolving vertices, and the other side has P. If we were to attach them by the vertex V, which we will identify in the beginning, then we can kind of contract the whole side into one. So we can kind of see this as having P plus 1 resolving vertices. If we remove one, it has P resolving vertices. And as we said, the red side has at least metric dimension P. So this could resolve the graph. But if we remove one more, then we're saying that it has P minus one resolving vertices, which is a contradiction because the dimension is at least P. Okay. So we can remove at least one from each side. Okay, now what about for the upper bound? Well, we're kind of going to call these problem vertices, which is two vertices that have the same distance vector. If they were in the same side, then this would kind of contradict us saying that this is resolved by P vertices. So they can't end up on one side. They have to be on opposite sides. And it turns out that there could be more than one. And this caused a problem, of course. But luckily, we were able to show that they all actually lie within the line. And so in order to fix this, all we really need to do is just pick one of the endpoints and it resolves all the other ones. Okay. For example, if these two have the same distance vector, well, then this one just be distance 2 and this one be distance 3. So we make them different. Okay. So what about the edge-deletion? Well, the edge-deletion was already solved by Eroh in 2015. It was shown that it can be bounded above. But in the same paper, they questioned what about lower bound? Well, I'm going to show by example that this can't be the case. So Machikira in 2021, they introduced a graph, which I will explain. Suppose you have a star graph below of size K. In this case, K is 3. And we have a spider graph of size 2 to the K. In this case, it will be 8 legs. Okay. And we kind of make every single combination that we can make possible. Okay. Or you can think about it as a binary composition. If we add this edge, then this turns out to have metric dimension 2K minus 1. But if we were to delete the red edge, then it actually goes down to K plus 1. So this kind of shows that there's no lower bound that we can find, or at least bound based on the metric dimension of G. For the edge addition, we kind of do the inverse operation. So there's a lower bound, but there's no upper bound. Okay. What about for contraction? Well, we were able to show that, again, there's a lower bound, but there's no upper bound. Okay, so we just use this graph, which is the same graph we used before, but instead the edge here has a vertex. And if we can show that this has metric dimension K plus 1. But again, if we were to contract the edge E, then it goes all the way up to 2K minus 1. So there's no upper bound for this. And the vertex split is the same case, but reversed. Okay. So there's no lower bound for the vertex split. So why exactly does this happen? Why exactly are both of them kind of similar in a sense? Well, consider a graph again and take its diameter to be D. Diameter is just the longest distance between two graphs. Sorry, the longest distance between two vertices in the graph. Okay, so take some resolving vertices in a vertex, and we input its distance vector. So the distance from any vertex to our identified vertex V. Well, it's clear that the distance from V to W has to be at least D. And so we can see that the size, the number of vertices is bounded above by dk, which because there can be many distance vectors, but it's of size dk. So, but what happens if we increase the diameter? Well, then we get this better bound, or I guess worse bound. No, I guess better. And there's a possibility of decreasing k. We can decrease k, and k, remember, is the metric dimension. So we can decrease the metric dimension. It's possible to decrease it. But if we decrease the diameter, then this makes everything more compact. And so there's a possibility of increasing K. And so if the diameter increases, then the metric dimension can go down. And if it decreases, it can go up. And this exactly lies with what happens in the edge deletion. And edge deletion will can increase the denominator, and the vertex split can as well. And the edge deletion can decrease the denominator and as well as the edge contraction. Okay. And so our main theorem was also that if we successfully apply these operations, then we can get this upper bound, which we were able to find that is sharp. Okay, one for the vertex split and another one for the edge contraction. We can get similar results for the edge deletion and the edge addition. Okay. And we
simple graph?
Yeah, sorry.
What is a simple graph?
It's any graph that doesn't have a loop, so like a self loop or multi-edges or disconnected. Okay, or well, no, just yeah. Yeah, very second doesn't. And we showed that these bounds are sharp. For example, take the following graph. We were able to find that this has, well, for each component, we only choose 2 of them. And it's enough, if we do that successfully, then it's enough to resolve the whole graph. And if we apply some contraction on the center, then we can increase each side by 2, by at least 2 vertices. If instead we delete an edge, this one for each one above, then we can increase each time by 2. And so it shows that the bound is sharp for all 4 operations. And of course, we can just pull it back to get the other results. There was also other families we were able to define. For example, DKR. K is just the number of vertices on the star, in the bottom, and R is just the number of spider legs. And then similarly, we can find EKR, which is just
Sorry, can I answer the question? Because
Yes.
we had this picture before. Is the bottom supposed to be completely connected to the top and just didn't draw all the edges, or is there a special way you've attached the star to the spider?
No, you can just, I mean, the way they define it in the paper, they use a binary composition.
Although it's like a.
But I just did it a little bit easier so you can see what's happening. Yeah. But we don't.
Can you repeat what you said? How do you connect them?
Based on like binary composition, for example, this represents 0, so that nothing's attached to it. This represents 1, so the first one's attached to it.
Oh, okay. Thank you.
So this is what DKR is, and EKR is the same thing, but with a line. And then FKR is the same thing, but with a vertex in this edge. And with these graphs alone, we can find some more results. For example, given any metric dimension of EK, we can make it go as high as we want with some bounds. And similarly, we can double or triple the metric dimension if we wanted to. Okay. And that's my thought.
So you said the main goal was to try and understand metric dimension for excluded K4s.
Yes.
And I didn't know, is excluded K4s the exact same thing as outer planar?
No, it's the same thing as series parallel networks.
Series parallel.
Mhm.
So those were the graphs that could be created by introduced loops or split up the edges into.
Yes. Yes.
Can you give the example, but it was basically like an exponential log away from the relevant bound that you wanted? Is that the worst case scenario? Like you said, there was no upper bound or.
Yeah.
It's like, is it an exponential upper bound or a log lower bound, or could it get even worse?
Apparently it's really hard to find examples that can get really bad. I'm not sure if that's the highest we can go. I mean, based on us doing just binary, that seems to be the limit. But I'm not sure if we can go even higher than that. So I don't know.
It's an NP-complete problem, so maybe. And let me add one more thing. So David, there's a long history of metric dimension papers and long history of minor papers. And what David is doing is blending these two fields together. So
So I have a question.
Yeah.
So when you mean there is no lower bound or upper bound, you mean there's no interesting lower bound and upper bound, right? Because you always lower
Yeah.
bound by zero and upper bound by the number.
Yes. Yeah. Oh, you can actually bound them by the denominator, but that's not really interesting because it's not. Yeah. Yes.
Are there any open operations where you don't know the exact change and it's not tight? Like you had a like a +2 or -2 and it was tight, you said. Yeah, are all the operations understood?
the first speaker's operations,
Yeah.
open problem.
I would bet that it increases. Based on what?
For which operation?
Swing
Compression.
Okay.
Oh, for the operation we were talking about, I was talking about the vertex amalgamation, but we can amalgamate it by click sums instead. And so far we've have some proof, but we haven't checked it.
Any more questions? So how should we do this?
Yeah.
Yeah, so